Listo.
Entonces, la última sesión de este congreso comienza con una charla de Andrés.
Okay, in English, yeah. Thank you very much to the organizers for the opportunity to be here, for all of you to be interested. It's a pleasure to be here in Mexico and in this conference. So the purpose of this talk is to present you a geometric construction of non-representable classes. So Tom in the 50s showed that there are homology classes that cannot be represented as the push forward of the fundamental class of a closed manifold. And his construction is not geometric. He gives some obstructions to the existence of a manifold such that the fundamental class push forwards to a homology class, and he shows that there are some examples of non-representable classes. I will try to explain how they look and why they are not representable. This was in the 50s, so I'm not the first one who has tried to understand these classes geometrically. So here is a extract from paper from Dennis Sullivan, Singularities in Space, 1966, and he's trying to understand the counterexample of Tom. How do they look like geometrically? And as we will see, these classes live in the 7 homology of a product of Eilenberg-MacLane spaces. And Sullivan explains that the singularities of this homology class that he denotes like this, look like a surface times the cone on CP2. So we'll show a construction that will make it clear, what is the surface and why the cone on CP2. Somehow this talk is going to be very basic. And every time I give it, I start feeling like, oh, maybe it's too trivial. But then I recall 2 phrases from Gromov, especially the second one. Trivial is relative. Everything that you understand after 2 minutes, you start thinking it's trivial. But somehow I feel that it's important, to share trivial things, especially because they're beautiful. So maybe you think they're trivial, but at least I hope you share, that they are very, very beautiful. So, in algebraic topology, we assign algebraic invariants to spaces. We have seen many of the classical invariants here, homotopy groups, homology, Bordism, K-theory. From those invariants, homotopy groups, K-theory, and Bordism are very geometric. Homology is more algebraic. And Steenrut's problem is the question if every invariant that you can define in homology algebraically somehow can be really defined geometrically. So let's talk about Bordism. Bordism, main tools of algebraic topology, the fundamental question is when is a manifold the boundary of another manifold? So definition of when 2 manifolds are cobordant. We say that 2 manifolds are cobordant if they together share the boundary of another manifold. As Carlos was explaining his talks, here we have maybe M1, maybe here we have M2, and we say that they are cobordant if they together are the boundary of n+1 dimensional manifold with boundary. And actually this defines an equivalence relation on the class of n-dimensional closed manifolds, and that set can be endowed with an operation that is the disjoint union. So actually we have a group, and when we denote this group by n, the nth cobordism group of manifolds. So actually, since you can take any manifold, closed manifold, and cross it with the interval, you have any m, you cross it with the interval, and the boundary of m cross I is 2 copies of m. You can see that this group is actually a vector space over Z2. the inverse of an element is the element itself. So actually, let's see some simple examples. Carlos mentioned some. Zero-dimensional compact manifold is a set of points, finite set of points, and we know that 2 points are the boundary of an interval. And we know that 1 point is not. So that proves that the zero-dimensional covariant group of manifolds is C2. Every one-dimensional closed manifold is a finite union of circles. Every circle is the boundary of a disk, so this is 0. Every two-dimensional oriented manifold, we know, we classify them, so there are surfaces, some genus, we can make them the boundary of three-dimensional manifold. When you have non-oriented manifolds, things become more interesting. RP2 is not the boundary of a manifold, and actually is the generator of the second covariant group of manifolds. Exercise, like prove that RP2 is not the boundary of a manifold, but just suppose it is, double the manifold, and calculate the Euler characteristic. That's actually the solution to the exercise. Not so easy, actually not. Every closed three-dimensional manifold bounds. That's the result of rolling. Classical Thom-Triagin theorem tells us that the covariant group of manifolds can be identified with the stable homotypic groups of a spectrum, MO. And actually, with this identification, Thom can calculate these stable homotypic groups and proves that this covariant ring of manifolds, now we take the Cartesian product of the classes, is a polynomial algebra over C2 with some generators, given in some degrees. For n even, you can take Rpn to be a generator, and for n odd, you can take some hypersurfaces. That's just to show you some of the beautiful results of Thom. We can do the same thing with oriented manifolds. Like the only thing is that now if we take into account the orientation, we have to reverse the orientation on one side. Remember that when you take a cylinder of an oriented manifold, now that the boundary of this cylinder has a minus here. So actually now the inverse of a class in the oriented covariant group of manifolds is the manifold with the reverse orientation. Some examples. Now, zero-dimensional manifolds, if they are oriented, are points with orientations, plus or minus. And we know that a point with a plus and a point with a minus is the boundary of an interval that is oriented. So what we take now is the number of positive points, the number of negative points, we subtract, we get an integer, and that gives the isomorphism between zero-oriented covariant group of manifolds and the integers. We already said why omega 1 is 0. We already said why omega 2 is 0. Rolling again, omega 3 is 0. Every three-dimensional oriented manifold bounds an oriented manifold. And more than an exercise, CP2 is not the boundary of an oriented manifold. Actually, it's the generator of omega 4. Now, the invariant that we use to prove that this guy is not a boundary is the signature. Okay, same Thom-Triagin construction, but now taking into account the orientations, give the identification of the oriented covariant group with the stable homotypic group of another spectrum, MSO. This one is a lot more complicated, and actually Thom managed to calculate the oriented covariant ring of manifolds when you tensor with the rationals. It's a polynomial algebra over the rationals with some generators in degree 4i. Generators can be taken to be the CPNs for n even. And for example, this calculation can be used to prove the signature theorem and to give one of the earlier proofs of the index theorem. So these calculations are very important. So later on, big names, Milnor, Novikov, Wall, completed the calculation of the torsion part of the oriented covariant ring or group. So Milnor proved that omega star has no odd torsion. That's going to be crucial for this talk. Novikov calculated or identified the torsion-free part of the covariant ring of manifolds. It's a polynomial ring over the integers with generators in dimension 4i. And finally, Wall described this guy, the oriented covariant ring, in terms of another guy W, that is the subalgebra of the unoriented cobordism ring, where the elements have representatives such that the first Stiefel-Whitney class is the reduction one integral class. So if something is oriented, the first Stiefel-Whitney class is 0, so this is more general. And this subalgebra, now called the W of wall, fits into a long exact sequence that you see here, multiplication by 2, thinking of an oriented manifold as an element of W, because it's also an unoriented manifold, but the first Stiefel-Whitney class comes from the reduction one integral class. And actually, this long exact sequence is the key to Wall's calculation of the oriented cobordism ring. Actually, this exact sequence generalizes an exact sequence of rolling relating oriented cobordism groups and non-oriented cobordism groups. We were talking about just manifolds, but now we get a generalized homology theory. You know, was Atiyah the first one to consider the generalized homology theory and cohomology theory associated to MSO. And actually, he explained the sequences of Wall, rolling, and I think there was another one of Dold, in terms of these generalized cohomology and homology theories. And this is basically one of the main objects in this talk. So what is it? Well, we just take closed manifolds, continuous map to X, and we mod out by the Bordism relation. You know, it's like the standard thing that you would think. These guys form functors, and actually this extends to a generalized homology theory. And when you evaluate at a point, well, you get the cobordism ring of manifolds. So this is Bordism theory of a space. It's a funny thing about the names, you know, like this is the cobordism ring of manifolds, and this is the Bordism of a space. But it is historically, yeah. And every closed manifold has a fundamental class in homology with C2 coefficients, and now you have a map to X, and you do the push forward, no? And then defines a natural transformation between the Bordism group of X and the homology with C2 coefficients. And similarly, you can do the same thing with oriented manifolds, and you define a homology theory called oriented Bordism of a space X. Every closed manifold has a fundamental class with integer coefficients. You do a push forward of the fundamental class along a map, and you get a natural transformation between Bordism and homology with integer coefficients. What is Steenrod's problem? If these maps are surjective. Is every homology class here the image of a guy here? That's Steenrod's problem. And Tom's result. With C2 coefficients, every homology class is realizable by an element of Bordism group. He can prove this because he knows the homotopy type of the spectrum MO. You know, it's a product of Euler-Maclaurin spaces, and he looked at some piece, and he can show that this map is surjective. But MSO is more complicated. No? And actually, Tom proves that for integer coefficients, this map is not necessarily surjective. Actually, he gives an example in the homology of BC3 times BC3. There in up to 6, our classes are representable. And in dimension 7, there is a class that is not representable. And I want to show you that class. Okay? So later on, Conner and Floyd were studying equivariant Bordism. So they started studying maps of prime order, so actions of ZP. And they proved that, can I have myself? That the Atiyah-Hirzebruch spectral sequence for oriented Bordism degenerates if and only if this map is surjective. So if Steenrod's problem has an affirmative solution, then this spectral sequence has all differentials equals to 0 from R equal 2. And actually, I'm going to show you a proof because I think it's really nice. So one first step is identify this homomorphism that I described in terms of the spectral sequence. Is the edge homomorphism between Bordism and homology. And you can see here that this comes from this group. It's part of the filtration of the spectral sequence. There is a surjective map here an isomorphism, and an inclusion. And these inclusions come from taking kernels of the differentials. So if all the differentials are 0, there is an equality here, and this is surjective, and this is surjective. So it's obvious that if the differentials are 0, then the Tom map, as I call this mu, is surjective. The interesting thing is the other direction. If the edge homomorphism is surjective, then all the differentials are 0. And let me show you this. So Conner and Floyd showed that the Atiyah-Hirzebruch spectral sequence for oriented Bordism degenerates for every space, but mod C. This is a third class of the torsion abelian group whose elements are of odd order. That means that all the differentials are odd torsion groups. And this comes from, the deep results of Wall about MSO. So here is, where deep things are used. And it's a general fact that the differentials are torsion, but that they are odd is the extra thing. So suppose that the mu is surjective, every homology class comes from a manifold, then we have that this differential is 0. But this is just for the edge, it's the edge homomorphism. So we look at the general element of the E2 page, is the homology of X with values in the cobordism group of manifolds, but by universal coefficients. Non-naturally, this is the homology with integer coefficients, tensor the cobordism group, plus a torsion part. But this hypothesis that this differential is 0 says that on this part the differential is 0. And using this, that the differential is an odd torsion group, and the fact that this guy, omega q, has only even torsion, gives that the differential here is 0. This is for E2, but you do the same thing for E3. So this is what I was saying, like E2PQ is E2P0 plus a torsion, but this is even torsion and differentials are odd torsion, so that's it. Beautiful. Now, let's go to the examples. Homology of BC3. Here is not the counterexample of Tom, but this will be very important. So we know BC3, classifying space of Z3 principal bundles. We have a geometric model, the infinite length space. You have a cell decomposition, you calculate cellular homology, and you get this calculation. And actually, you get the generators of the homology. We get that for n odd, this C3 is generated by length spaces. Yeah? Length spaces with inclusion to BC3. So this map is surjective because we have the generators and we know they are manifolds. So this map is surjective. So actually, by the theorem of Conner and Floyd, the spectral sequence degenerates. Also, and that's why Z3 is great, this homology has only odd torsion and omega q has no odd torsion. So when you calculate the E2 page, again, this gives homology with integer coefficients, tensor omega q plus a tor. But this tor is 0 because odd torsion, even torsion. So just get this guy. And you go by induction and you see that since the length spaces generate this part, well, they generate 2, and then you go on, and then they generate the Bordism groups. So the length spaces are generators of the Bordism groups. And just let me tell you that those elements have orders that are not so easy at the beginning to understand. Actually, these length spaces have order 3 to the a plus 1, where a basically is the floor function of 2n minus 1 over 2 plus 1. So basically, S1 mod out by Z3 has order 3, 3 to the 1. S3 mod out Z3 has order 3, but S5 has order 9, and it goes up. And this shows that there's something more difficult about Bordism than homology, because the homology of BC3 is group homology is killed by 3. The order of the group kills group homology. So every element should have order 3 in the homology, but in Bordism we have these funny orders. Okay, so that was about representability with integer coefficients, Z2. Let me talk about representability with CK coefficients.
The oriented Bordism groups, are their relations known for the product of manifolds?
Oh, don't know completely.
The complex case, that is not.
The BC3 times BC3?
No.
This guy?
You told us as a module, but it's
Yeah, this guy, so this.
yes.
Yeah, actually, Conner and Floyd, in his book of differentiable periodic maps, at the last section of the book, says, this guy has projective dimension 1 and is equal to something with these relations. And I will talk about the relations later on. So let's talk about Steenrod's problem with CK coefficients. So for C2, it was unoriented manifolds. For integer coefficients, it was manifolds, oriented manifolds. How about C3 coefficients? Well, Sullivan introduced CK manifolds. As a special case of manifolds with singularities, he was interested in index theory with mod K coefficients. So what is a CK manifold? CK manifold is a manifold with boundary such that the boundary is K copies of the same manifold. And this is an example of a C3 manifold. This is an example of a CT manifold. And actually, Sullivan thinks of a CK manifold as the space that you get when you glue the two copies of this space. So for example, a cylinder of the Klein bottle. Or in this case, take these 3 circles and glue them. And you start having spaces with singularities. I don't like to think like that. So for me, this is a CK manifold, and there's an underlying space that is the quotient space. Like with orbifolds, and I don't like to take the quotient space, I like to keep track of the information. So some examples, same picture here. So I have a manifold with boundary. The boundary is 3 copies of the same thing, and I have maps given that identification. You can take the quotient space where you identify, and so cylinder as a C2 manifold, and depending on the identification, you get a torus or you get the Klein bottle. So those are the objects. Now I want to talk about the Bordisms. Bordisms are a little bit more complicated. It's a manifold with boundary. In the boundary, we take K copies of a manifold and we take them out. So let me give the example that is going to be there. So imagine D3, the boundary of D3 is S2. In here I take 3 disks and I take them out. And what I get is the pair of pants. No? So basically that's a CK manifold with boundary. Manifold with boundary and a thing that is N. K, disjoint orientation preserving embeddings of N into the boundary of M. And like when I erase those K things in the boundary, I get a CK manifold. So the boundary of this guy is the pair of pants. Probably it would be good to have a look at it like this. But this is CK boundary of that thing is that. And that defines CK manifolds with boundary, and you can talk about Bordism of these guys, and that defines, well, this is another picture. This defines ZK Bordism. This was defined by Sullivan. And the thing is that CK Bordism sits in a long exact sequence called the Bochstein long exact sequence, where here you have Bordism, oriented Bordism, multiplication by K, reduction math K, I will say something about that in a moment, the ZK Bordism, and the Bochstein. So what is the Bochstein? Remember that this is a CK manifold. The boundary is 3 copies of the same thing. So the Bochstein, I'm going to do this again, Bochstein of this is just a circle. The Bochstein of this is again a circle. So, in words, what I'm doing is taking the boundary and dividing by K. If you know the Bochstein of homology, is taking the boundary and dividing by K. So it's a geometric interpretation of that operation. Funny thing that is well known to the experts, but I cannot really find it, is that C2 Bordism of a point is the W of wall. Now, if you see this long exact sequence and you put 2 and you see the long exact sequence of wall, you say like, well, and actually there is an isomorphism between those two long exact sequences that is not completely obvious, but it's also not difficult. But you take W. What is W? It's like unoriented manifolds where the first Stifel-Whitney class is the reduction of an integral class. That information gives like where to cut and open, and that gives a C2 manifold. And you work a little bit, it's not completely trivial, to show that actually that is an isomorphism. The inverse is easier, it's just take this guy and glue, but still. Okay, this CK-Bordism relation extends to a generalized homology theory that is called the CK-Bordism of a space. And Sullivan, in a paper with Morgan where he introduced CK manifolds, says, obviously, but no, he didn't say obviously, but CK manifolds have CK fundamental classes. Where is not in these spaces, he's thinking about the quotient space, but actually in the quotient space, there is something called the fundamental class with CK coefficients. And with that, you can define a natural transformation, and there is a morphism of Bochstein exact sequences. Here is Bordism with CK Bordism, and here is homology. This is the usual Bochstein long exact sequence coming from this short exact sequence of coefficients. And here is just, like push forward the fundamental class, push forward the fundamental class. So it's very natural. Turns out that not every homology class with CK coefficients is in the image of this map. So actually here the space is simpler. For BC3 with C3 coefficients, the classes up to 5 are representable by C3 manifolds, and the first non-representable class is a generator of H6. So I'm going to show you two things, the generator of H6 and the singularities, and the counterexample of Tom, or a cousin. I will tell you why, maybe not Tom's, but a cousin. So let's look at the homology. This is very trivial. Homology of BC3 with C3 coefficients is C3 for all n. Let's look at generators, geometrically. So Bochstein long exact sequence, multiplication by 3, reduction mod 3, the Bochstein. So what is this reduction mod 3 in terms of CK manifolds? So think that, maybe I should have said it before, but oriented Bordism, C3, Bordism. Every oriented manifold can be seen as a CK manifold. Just take the empty set as the K copies of the boundary. So that's reduction mod K. And we know, cellular or group homology, that multiplication by 3 is the zero map for n greater than 0. So this Bochstein long exact sequence breaks into two pieces. For n odd, we have an isomorphism given by reduction. And for n even, we have an isomorphism given by the Bochstein. But since reduction is just seen as a closed manifold, as a CK manifold, we know the generators here are given by the length spaces. And for n even, we know that we want generators here such that the Bochstein are the length spaces. But what is the Bochstein? The Bochstein is divided by K. So what we need is manifolds with boundary, 3 copies of length spaces. So let's look for them. And here is saying generators for n odd are now I'm not thinking about length spaces, but the principal bond over it. Sphere with the standard action of Z3. Alpha 2, first one that is not a closed manifold, should be a surface with boundary with an action of C3 such that the boundary is 3 copies of S1 with the standard action of S3. And let me show it to you. So here what we have is R2. I have a lattice. It's not like the lattice generated by E1, E2. It's generated by E1 and the rotation by 120 degrees of E1. And what is good about this lattice? That actually there's an action here of rotation. It has fixed points, but no matter what, I take the quotient of R2 by the lattice and I get a torus. And this rotation gives an action of C3 on the torus. The fixed points of that action are shown here. So rotation always fixes the origin. So that's a fixed point. But there are other points, like 1, that when you rotate 120 degrees, is one distance apart horizontally. So in the quotient space is a fixed point. There are other points here that when you rotate 120 degrees, are separated one distance apart in that direction. So in the quotient space, you have 3 fixed points. You can calculate them. You take the torus with those 3 points, you erase disks around those 3 points, and you have a surface with boundary, 3 copies of circles. And that's it. That's alpha 2. Who is alpha 4? Alpha 4 should be a 4-dimensional manifold with boundary, 3 copies of S3, with the action, standard action of C3 on that. So you take CP2 with this action. This is the generator of Z3. This is row to the 0, row to the 1, row to the 2. You calculate the fixed points, are 3 points, 1, 0, 0, 0, 1, 0, 0, 0, 1. You take shards. You look at the action around those points, and you see that is this. This doesn't look like the standard action of C3 on C plus C, but after orientation reversing diffeomorphism on this part, you get the standard action. So the generator alpha 4 is minus CP2 when you erase 3 disks. For alpha 6, we need singularities, and that's where our counterexamples to the Steenrod problem appear. So here comes to the relations, Bernardo. So Conner and Floyd, in his book, were studying, these are free, Bordism of free actions, reduced. And Conner and Floyd studied the omega star module structure of this guy. And they proved that we know the generators, spheres with the ZP action, or length spaces, if you want to think like that. And they constructed some manifolds, M2, M4, M6, M8, and so on, such that there are these type of relations in this guy. This looks complicated, and that's why I like to present everything with 3. Let's put P equals 3, N equals 3. Actually, if you read their construction of Conner and Floyd, M2 is the torus with the action that I just described. M4 is CP2 with the action that I just described. And the relation, this relation, is this relation. 3 times alpha 5, the 5-dimensional sphere with the standard action, plus S1 cross CP2 is 0. So 3 times alpha 5 is minus alpha 1 CP2. So if we find someone whose boundary is minus S1 cross CP2, we have the generator in dimension 6. This is not possible with manifolds because CP2 is not the boundary of a manifold. But it is possible with singularities. And how do you do that? Well, if you see that what I want to do is get a thing such that the boundary is S1 cross CP2, what you do is S1 cross the cone of CP2. So we all know the cone, but now we want to think about the boundary of the cone. But if I take M and I do the cone, and I'm going to do it horizontally, this is just M. Yeah. So one easy way to make something the boundary of another thing is just by taking the cone. So I take alpha 6 to be minus S1 cross the cone of CP2. And you're saying like, if you're just going to take a cone, why don't you cone everything? And the thing is because we are working in the Bordism group of free actions. So we want a free action. If I cone everything, this guy is fixed by C3. But if I take S1 with a free action and I cross it with whatever, it's a free action. So the fact that 3 times S5 is a product allows me to make a cone and still have a free action. So this guy is a thing. It's not a manifold, but it's something with a free action such that the boundary is 3 times alpha 5. I'm lying a little bit because this is an equality here. So actually, what is really happening is that in H6, B, C3, C3, my generator is, here I have minus S1 cross CP2, I do the cone. So this is cone of minus S1 cross CP2. And there is some funky bordism, 2, 3 times. This is 3 times S time. Yeah? Recall that this is with actions, with free actions, no? So this is the counterexample to Steenrod's representability problem with C3 coefficients. Yeah?
But didn't you say that precisely the cone point is a fixed point?
Hmm?
The point of the cone.
Gracias. Because I'm saying nonsense. This is minus S1 cross the cone of CP2. So this picture is not completely accurate. You know, like my, what is that? 6-dimensional picture in the plane is a little bit lying. So just because I mentioned the orders of the guys, I said that alpha 5 should have order 9, and that's because 9 times alpha 5 is 3 times 3 times alpha 5. 3 times alpha 5 is minus alpha 1 cross CP2. I put this 3 here, and 3 times alpha 1 is the boundary of this torus minus 3 disk. And you can prove that 3 times alpha 5 is not 0. So.
But in this CP2, the actually 3.
No, it's not 3.
It's not the CP2.
No,
it's the CP2 of M4, which comes from the borders from the coefficients.
Yes.
So the action is 3 times it. You put it 3 times.
Okay.
Or not?
I didn't get the question.
Is a C3 space? So
CP2, actually, these M's have CP actions but are not free, and you can even think that they are like the trivial action. It doesn't matter which action you put.
But didn't you just tell me they come from the coefficients?
The what?
They come from the coefficients. From omega.
Yeah, they come from the coefficients. So when you take something in the coefficients and you put it like that, you put 3 times CP2 with a trivial action. Okay. So back to the homology, H7, BC3 with integer coefficients. That's where Tom's counterexample is. So here we have Kunet exact sequence. The part that we know easily, the tensor product of this homology, and something in Tor of these things. So the good thing about the Kunet exact sequence that it splits, not naturally, but still splits. And actually you can calculate that in H7 of this guy, there is a basis with 5 elements. It's difficult to read, but here is just the part that comes from Kunet, here and here. 1 times 7, 7 times 1. And the thing in the middle are things that come from the Tor. Yeah? But I will describe them geometrically. So you see here is alpha 2, here is alpha 6, alpha 4. Those were classes with C3 coefficients, but I'm saying that these things are with integer coefficients. And that's because, if you calculate the boundary of these things, this is like this little piece, this gives you something, and the boundary of the other part gives you the negative. So when you add, there is no boundary. Yeah, so alpha 2 times alpha 5 plus alpha 1 times alpha 6 has no boundary. You can glue those two things. You have a closed thing, and if you look at this, alpha 4, alpha 3, alpha 3, alpha 4, only manifolds. Alpha 1, alpha 7 manifolds, alpha 7, 1 manifolds. Where are the singularities? Where alpha 6 is. So actually the singularities of this guy, alpha 2 times alpha 5 plus alpha 1 times alpha 6, are of the form what? Here are no singularities. This was a surface. This was a 5-dimensional sphere. It's here. But what is this? Alpha 1 is a circle. What was alpha 6? A circle times a cone CP2. This is minus S1 cross the cone. Sullivan says that it was a surface times the cone CP2. So this is like a more explicit construction of the singularity. So, working with things sounds a little bit fishy. So you have to, how do you work with singular things? But you are going to ask something.
What was the manifold?
It's not a manifold.
It was a manifold.
It's not a manifold because it's not representable. But it's, like alpha 2. Alpha 2 is torus minus 3 disks. Alpha 5 is 5-dimensional sphere. Alpha 1 is a circle. alpha 6 is a circle times the column CP2. This is the thing.
So what is the class that's the only class?
No, well,
classes
no. There is here, and there is like kind of the reversal. Alpha 6 times alpha 1 plus alpha 5 times alpha 2.
But the other,
And the other ones are just manifolds. So when I started, I said, let's look for how Tom's example looks. But actually, I don't know which one is Tom's example. But we believe Tom, so here, one of them should have singularities. And this guy has singularities, that guy has singularities. Could be a combination, but. Yeah? Okay. So, how do we do Bordism theory with all objects with singularities? Well, Sullivan and Bass have a whole theory of manifolds with singularities, whole thing. There is a more recent thing by Führing, a student of Hanke. He develops a smooth version, thinking about applications to positive scalar curvature. Craig has a theory of stratifolds. That's the one that I used. And the good thing about stratifolds is that it gives a Bordism theory that represents a homology with integer coefficients, homology with C2 coefficients, And the good thing is like you can talk about smooth functions. You have regular values. You can take the pre-image of regular values. So a lot of the techniques of differential topology for manifolds are applied there. So with stratifolds, Hagaita, a student of Craig, gives the Postnikov tower of oriented Bordism in terms of stratifolds. And like when you express the Postnikov tower in terms of something, then you have an interpretation of the Atiyah-Hirzebruch spectral sequence in terms of those guys. So basically what Tene gives is a description of the Atiyah-Hirzebruch spectral sequence for Bordism, oriented Bordism, in terms of stratifolds. And what we did with Carlos Segovia and Arley Fernando Torres is define CK stratifolds, prove that they have CK fundamental classes, that the Bordism theory satisfies, Mayer-Viatoris and the axiom of a homology theory, and interpret the Postnikov tower of CK Bordism in terms of CK stratifolds. So that's it, basically. But you see, I'm lying a little bit because I'm telling you, look, this guy has singularities and that's it. But you can ask, well, maybe there is a Bordism of this thing to a manifold. So how do you know that, this guy, this singularity cannot be removed? Well, because Tom proved that there are, counterexamples. But actually, we don't need to use, Tom's argument that there are counterexamples. The good thing is that, like if we have an interpretation of the Atiyah-Hirzebruch spectral sequence in terms of stratifolds or CK stratifolds, we know how to prove that a homology class is not representable by a manifold. Just calculate the differentials of the spectral sequence of Atiyah-Hirzebruch and prove that is non-zero. We all know that, it's so easy, to calculate differentials of the spectral sequence. But that's the great thing about stratifolds. You have a geometric description of the differentials. And I have time, but I'm going to stop here to ask for questions. And depending on your questions, I decide what to say. If there are no questions, I also decide what to say. But
It's a riddle.
no, you don't have to clap because I'm going to continue. Questions? I'm not going to escape so fast.
It's a riddle.
Questions?
What do we ask? Tell us what to ask. So
How about your question? It may not make sense, but you're going all the way to cobordism, but you could stop in the chromatic K-theory.
Okay.
How does K-theory look like this?
I don't understand your question, but I'm going to say something in any case. K-theory is a cohomology theory, can be represented by vector bundles. There's a definition with vector bundles. There is a homology theory that can be represented with Bordism theory. It's the Bordism theory of spin C manifolds with blah, 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 blah. So you could try to ask these things with K homology. And I think the ideas that I will show you soon on how to get the Postnikov tower of Bordism theory can apply to give something. It's not the Poisson tower. I already tried, and it's not the Poisson tower, but it's like kind of a relative tower for K homology. So in principle, I think there is a spectral sequence converging to K homology. Is not the Atiyah-Hirzebruch spectral sequence, but should be related to spin Bordism with singularities. The thing is, like, the representation of K homology is spin Bordism and some modification, spherical modification. So it's just not only Bordism. More questions?
Any homology theory can be represented as some kind of Bordism, right?
Yeah, that's the kind of point of Bas-Solimat manifolds. Like, you can just start with the MU, for example, and you say I want a generalized homology theory where the coefficients are that ring, but these things now are 0. So you start like putting cones, so you kill those manifolds and you get a homology theory, and you hope that that represents the one that you want. More questions? Okay, so I have some minutes. So what are stratifolds? And so stratifolds are generalization of manifolds. Let's forget that. So are topological spaces with a sheaf of functions, subsheaf of functions. And the differentiability comes in one condition. If you take functions, K functions in that subsheaf, and you have a differentiable function from Rk to R, then this composite is inside. You know, like that's a differential space. And with a differential space, you can define the tangent space at a point, just in terms of derivations of the germs of functions. And they can have different dimensions. So you stratify your space by the dimension of the tangent space. And stratifold is a topological space that is a differential space. So you have a subsheaf of functions with that property that satisfies, you know, locally compact, Hausdorff, countable bases. The skeleton of those things defined with the dimension of the tangent space are closed, but such that when you take a point, that point lives in one of these strata. And you have the germs of the whole thing and the germs of, you know, of that stratum. You assume that those stratums are smooth manifolds and that the restriction of the global function to the function just on that stratum is an isomorphism. You also require that you can find partitions of unity, like Bank functions is enough for that, and that you want an n-dimensional thing that the dimension is less or equal than n, and the n-dimensional stratum is non-empty. So basically that's a stratifold, and the main example is taking a manifold and doing the cone, and taking a manifold and doing the suspension, taking two manifolds and do the join. So many things that you can do, but somehow I think from the perspective of singularity people, you know, taking the cone is too much, but you know, this is done for representing homology. And so the examples that I said, like a manifold, well, is a stratifold with just top stratum is everything. You can take the 1-point compactification. Something that is not so trivial is take two stratifolds, define a stratifold structure on the product. And if you think about it, it's like, okay, I know the smooth functions from S1 to R. I know the smooth function from S2 to R. What are the smooth functions on the product? We tend to teach in vector calculus, you know, that joint continuity is not enough, you know, joint differentiability is not enough. So how do you do that? Read Matthias Craig's book. It's not so easy, and I think it's very nice. But it boils down to knowing what a smooth function on the product of manifolds is. But you have to do some retractions. So an example is a cone, open cone. Because these kind of things would be with boundary, by the way. So there's one thing that is very useful with stratifolds, is that you can build them inductively, like CW complexes. You take a manifold W with a boundary and a collar, and you take a smooth map from the boundary to a stratifold, then you just attach, you know, this W using the F, and you can put a stratified structure here, you know? Smooth functions here are smooth functions on S and on W, and that, you know, on the color are, you know, kind of constant or compatible. With respect to what?
I mean, presumably, maybe I'm wrong, but there could be more than one stratified structure.
Ah, yeah, definitely there are more. You cannot distinguish, you know, the stratified structure from the topology.
So
Is yeah, I guess. Now I get the question. Yes, I think so. And, you know, we define, or Craig defines, P stratifieds are the stratifieds that can be defined, you know, inductively doing this. So you attach manifolds with boundary. You attach manifolds with boundary. And manifolds with boundary are easy to define, you know. Locally, they look like open sets in Rn or open sets in, you know, half space. But stratifieds are not defined locally. So how do you define stratifieds with boundary? It's not so easy. You have a space, you know, T. There's a subspace closed that is partial T. You know, the interior of T is, you know, what is not on the boundary. You need a color, you know, and that's it. With manifolds with boundary, the color came from the definition, because locally there are colors, so globally there are colors, you know, with some compactness. But here you have to talk about the colors in the definition. And that creates, you know, the technicalities in the proofs. You know, it's very important. You know, we have stratifieds with boundary. We can define a homology theory, stratified homology, as, you know, maps from stratifieds, closed stratifieds to X, more out, you know, Bordisms. And the thing is, like, since we can take anything and do a cone, you know, this is anything and this is the cone on S, and the boundary is S, well, everything is trivial. So I just define 0 in a fancy way. But, you know, there is a way to work around. We need to work with oriented stratifieds. Oriented stratifieds, you know, is like the top stratum has an orientation of Sn, but codimension 1 singularities are empty. So when you require codimension 1 singularities are empty, this example doesn't work for a point. A point is not the boundary of a manifold, but is the boundary of a stratified. Which stratified? Take the point and do the cone. The funny thing is that it looks like that, but with the stratified structure, this point is different from this point. If you take this is the cone point, no? This gives you a point. But look at this has codimension 1 singularities. So if you avoid codimension 1 singularities, this doesn't happen. And that's it. That's the way to get a Bordism theory. Yeah, I have been many times making a point the boundary of something in different ways, with orbifolds, with stratifieds. But, you know, like every stratified of positive dimension is the boundary of the cone, and that's oriented in that definition. So the stratified homology of a point is 0 in positive degrees. But for a point, you cannot do this, so you get the integers. So this guy, because it satisfies Mayer-Viatoris and whatever, is homology with integer coefficients. But actually, you can do better. If you use P stratifieds, you can prove that a P-dimensional closed stratified has a fundamental class with integer coefficients, and you do the push forward, and you have a natural transformation, and Craig shows that this is an isomorphism. So homology with integer coefficients can be represented by a Bordism theory of oriented stratifieds. If you don't require orientation at the top stratum, then you get homology with C2 coefficients. And here comes...
But that's still requiring that codimension?
Yes, always. Yeah. Otherwise you get 0. So with Carlos Segovia and Fernando Torres, we define CK stratifieds, is taking the definition of CK manifolds and stratifieds and putting them together. You have to be careful with the colors, because the definition of stratified with boundary is not exactly as manifolds with boundary, but we can define it. You know, this is longer than the previous slide with CK manifolds with boundary. And you can define the CK stratified Bordism relation. And important thing is that there is a Bochstein's long exact sequence relating, Craig's stratified homology and what we define as CK stratified homology, as with CK manifolds. And we prove, well, my student, his thesis proved, that if you have a closed n-dimensional CK stratified, there is a fundamental class in the quotient space, in the homology of the quotient space. Then you can do the push forward when the map is, somehow equivariant on the border. Like Sullivan identifies the borders and take continuous maps. So if I don't identify, I need a map such that it's equivariant on the border. But anyway, you push forward and we prove that this is an isomorphism. This is a homology theory, and at a point it gives an isomorphism, so we represent homology with CK coefficients with CK stratifies. Okay, that's good, but here comes like the Atiyah-Hirsberg spectral sequence. So what is the Postnikov tower of a generalized homology theory? And I think I'm going to assume that is connective. Bordism theories are connective. So I have a generalized homology theory, and I find more generalized homology theories with natural transformations between them, such that when I evaluated a point, I have an isomorphism up to some point, and then after that is 0. So at a point I truncate, and I keep truncating, keep truncating. That's a Postnikov tower in terms of generalized homology theories. And Hagai Tene, what he proved is that when you have a Postnikov tower of this kind, you can reinterpret the Atiyah-Hirsberg spectral sequence in terms of another spectral sequence, where the Postnikov tower appears here. This, but the good thing about this is when you have homology theory, Bordism theory. So if you have oriented Bordism, you can define the Postnikov tower of oriented Bordism using stratifolds. Oriented Bordism is, Bordism of manifolds, and homology is Bordism of stratifolds. Stratifolds have singularities up to dimension n-2, no n-1. But I can ask singularities up to dimension n-3, n-4, n-5. And if I go down all the way, I just have a manifold. And that's the Postnikov tower. That's what Hagai proved. The homology theories defined by Bordism theory of P stratifolds with restrictions on the codimension of the singularities is the Postnikov tower of oriented Bordism theory. And he gives a very nice interpretation, like the filtration of the Atiyah-Hirsberg spectral sequence for oriented Bordism along, the horizontal axis. Here is the homology, here is the filtration, is precisely, the classes in homology that can be represented by P stratifolds with singular part at most up to a point. So, like if you have a permanent cycle, no singularities is a manifold. But if you have more and more and more, well, you have these stratifolds with restrictions on the singularities. And the good thing is that this not only works for the horizontal axis, you can really interpret the whole spectral sequence in terms of this Postnikov tower, and even more, this is the key thing. The differential can be given. If you have a P stratifold, you have a P stratifold S with a maps to X. If you get an element here, what you do is you restrict to the boundary of the map that you attach on the top structure. And with this, if you look at this example and Tom's example, well, our version of Tom's example, you can see that you have this element in H7. So you imagine this in a H2 page, and you calculate the fifth differential. And because we know how to construct it, because it's S1 cross cone CP2 union, whatever, we know the attaching maps, and we know that the fifth differential hits the generator of the H2. So it's completely geometric, and it's non-zero. It's not represented. And what we did with Carlos and Arley is calculate the Postnikov tower for Bordism, this is wrong, with CK coefficients. So we take CK stratifolds and start putting restrictions on the singularities. That gives the Postnikov tower for K aught. Maybe if I don't say it, you don't see it, but this is a key thing, and it's because the oriented cobordism ring of manifold has no odd torsion. For K even, this doesn't work. I don't know the Pozdnikov tower of the wall thing. At least it doesn't work with this. And the same thing. We have a filtration of CK Bordism, and we can express the differentials, and we can calculate in this example the fifth differential, and the fifth differential on this guy gives S1 gives S1, which is the generator of the corresponding guy. So it's not 0. And that's it.
More questions?
Is there a current employed sequence for productions of stratiforms?
What kind of a exact sequence? Correr and Floyd. Like you mean when you restrict
To reduce
the isotropy groups?
the calculation of one producing group to producing group of another kind.
I think it's.
For example, if you have a smooth manifold with a proper action discrete group.
Yeah. I think the Corner and Floyd exact sequence and the Bogstein exact sequence are kind of the same thing. And is doing that. So I would say maybe the analog of the Corner and Floyd sequence for stratifolds is the Bogstein sequence. But that's not so satisfactory question. But because here the singularities, the only thing that I know about the singularities in general are the codimensions. So I just filter by codimensions and I get this. When I have actions of the group, I can talk about the isotropy groups and I do families of subgroups and I have mark control. But here I would need to filter by codimension and types of singularities. But I think with these guys, the types of singularities are not easy to list or classify or control.
Or in the case, one action you might classify.
You mean doing stratifold of BG?
Motions are, although the isotropy groups are finite groups, in some cases.
Yeah, I think maybe what you're trying to suggest is I mentioned oriented Bordism of BC3, like free actions of unoriented manifolds. You can take free actions on stratifolds, or you can take arbitrary actions on oriented manifolds, and maybe you look at the quotient, there are singularities. But I think if you take arbitrary actions and you look at the quotients, there is a Corner and Floyd exact sequence, but that's the Corner and Floyd exact sequence, and I wouldn't know how to mix it with stratifolds. But yeah, it might be possible to mix the two things. That's one thing that I would like, to look at equivariant stratifold Bordism groups. Free actions, that's just homology of BG, but arbitrary actions. That's a good project. More questions?
If you know kind of like the representative given class, you know by definition the class of to cover this, right? But what if you try to ask for the specific manifold? I mean, you fix a class and you say, can you represent this by sphere? Not by the class of the sphere. Can you say like there are invariants or something like that? In general, because I know that there are invariants in some cases.
All these techniques are up to Bordism, but I guess for spheres you can always try to say something, but I don't know.
Another obvious question. Just yesterday, Carlos, the collaborator, was speaking about some because. Because there's so many flavors of this, all the way up to the Colaboración hypothesis. And presumably, it would be interesting to ask this for the COPs at the stratiform level.
Yeah. Well, yeah. I think this is something that I would like to do is, here you're finding like the Pozdnikov tower of Bordism. I guess you can try to do this in a parameterized way. to find, I don't know if it's the Postnikov tower, but a filtration of the B's of the cobordism categories. I think you would need to do this parametrically. But here comes the problem, and that's why I haven't been able to do something. It's like with the cobordism categories, you take the manifolds and you embed it into Rn, and you do things inside Rn. With stratifolds, do they embed into Rn? What does it mean to embed into Rn? It's a little bit if you try to do cobordism of orbifolds. You can try to do these corner flow exact sequences. That I did that in my thesis. And you can try to calculate things, but if you try to do cobordism categories, you take an orbifold and how do you embed it? Where do you embed it?
So you would want to have kind of a Whitney theorem on a very
Yeah.
complicated universal Rn stratifold.
Yes, but I would like to do that too.
Okay.
More questions?
Does the space of that?
And then you can put a G and, and metrics.
No more questions? Many thanks.